And I'm Colleen Naughton. Nutrients such as nitrogen and phosphorus are vital for life on Earth. They are what plants take from the soil to grow and provide us the fruits and vegetables we are eating today.
Did you know that approximately 29.2 million tons of phosphorus was mined from the Earth in 2012? This compares to 210 million tons of phosphorus mined for the whole world. As population grows, we need more food, and more food means we need more nutrients. Some researchers predict that our accessible reserves of phosphorus will be gone within 50 to 100 years. With energy and water becoming more precious resources, industrial processes like the Haber process to recover nitrogen can become costly. Current practices to obtain nutrients from fertilizers makes one wonder about the environmental impacts and the economic costs. Although we're worried about running out of nutrient reserves, we waste a lot of them these days. We fertilize inefficiently, and when it rains, the stormwater runoff adds so much nutrients to our surface water that algae blooms. These algae blooms turn our waters green and limits the amount of sunlight needed for underwater plants to grow. As the algae die and fall to the bottom, microbes consume them. The microbes also consume oxygen, and eventually all of the fish and plants die. This phenomenon is called eutrophication, and the end result is a dead zone. An example of a dead zone is in the Gulf of Mexico that forms due to agricultural runoff that makes its way down through the Mississippi River.
Today we're going to talk about nutrient resource recovery, why it's important, and what we can do as a society to recover these nutrients in a sustainable manner. There are different levels at which we can recover these nutrients, from the city to the household levels. We'll let Mr. Philip Arbery explain how his company Ostera recovers these nutrients at the city level from a wastewater treatment plant.
Ostera is a clean water company that uses a technology that was developed at the University of British Columbia to remove nutrients, polluting nutrients from wastewater and convert those into a high-grade, slow-release fertilizer. Ostera is both cleaning the wastewater by extracting these nutrients from the wastewater, but also turning them into an end product that is far more efficient at being used as a fertilizer. We harvest the material, we dry it, and bag it, and we have finished product coming out of these vessels in one step. If it's not adequately treated and recovered, it can only end up in one place, and that's back into our environment. And in our environment, not being used as a fertilizer means that it causes nutrient imbalances in our waterways. And that causes eutrophication and other problems with algae blooms and really impairment of coastal waterways, which are absolutely essential to our way of life.
Phosphorus is essential to all life and one of the key macronutrients for crop, plant, and turf growth. Conventional phosphorus fertilizers are highly water-soluble, so they dissolve quickly into the soil profile. The problem is, plants can't absorb all that phosphorus at once. Plants seldom take up more than 25% of the phosphorus fertilizer applied in that year. The remaining 75% can react with iron and aluminum or calcium and become fixed or tied up and unavailable to growing plants. That is why soils that contain high levels of phosphorus can still have plants that are phosphorus deficient. Plus, any excess phosphorus can leach or run off, causing nutrient overload in adjacent waterways. Fortunately, there is a more efficient way to deliver phosphorus to your plants that also minimizes nutrient loss. It's called Crystal Green, a slow-release phosphorus with nitrogen and magnesium. Crystal Green nutrient technology is citrate-soluble. It dissolves slowly and is available when the roots need it. Here's how it works. When growing plants need phosphorus, the roots produce organic acids, like citrates. These citrates activate Crystal Green nutrient release. Unlike conventional phosphorus fertilizers, which are water-soluble, Crystal Green's plant-activated granules respond to organic acid production, releasing nutrients gradually into the soil solution to meet plant demand instead of getting tied up in the soil. As plant demand decreases, nutrient release from crystal green is reduced, minimizing excess phosphorus in the soil and lowering the risk of leaching and runoff. And when the roots require more nutrients, crystal green is there to provide a season-long source of plant-available phosphorus when the plants need it most.
Simply amazing what they're able to produce from a wastewater treatment plant. Where I'm from, in Miami-Dade County, a new company just opened that is composting sludge. They dry it in a greenhouse and then they sell it to the local citrus farmers. Homestead Organics, as the biosolid fertilizer being marketed, will be sold at $5 the 40-pound bag. For the farmer, this is about $12 cheaper than buying from the chain stores. I imagine they're losing a lot of nutrients from the liquid waste though.
Yes, we humans do pee a lot per day, approximately 0.8 to 1.6 liters. That's enough to fill this water bottle. In the state of Florida, a population of 19.3 million, that's enough to fill 8 Olympic-sized swimming pools per day. In the world, with a population of 7 billion, that's enough to fill over 2,800 swimming pools. At USF alone, with a student body of 47,000 students, that's enough to fill 408 barrels a day. So even if your wastewater treatment plant isn't equipped like those in the Ostera video, you can recover these nutrients at the source, or building level. Let's hear from Kelly and Stephanie at the University of Florida for more about this.
As we embrace the importance of removing nutrients from wastewater, as well as recovering them for reuse, we have to ask ourselves, where are all these nutrients and wastewater coming from?
At a typical municipal wastewater treatment plant, our urine accounts for greater than 50% of the total influent phosphorus load and greater than 80% of the total influent nitrogen load. However, urine only contributes approximately 1% to the total influent volumetric flow. These disproportionate impacts of urine on the quality of combined wastewater are a result of the fact that urine is very nutrient rich.
Typically in the United States, our urine is flushed away every day with high-quality potable water, and then mixed with other waste streams, such as those from our washing machine, sinks, and shower. That entire mixture is then conveyed to a centralized wastewater treatment plant. However, due to the nutrient content of urine, alternative wastewater systems including urine source separation are being explored.
Urine source separation is the collection and treatment of urine as a separate waste stream through the use of urine diverting toilets and urinals. Urine source separation allows us to target high concentrations of nutrients for recovery while only dealing with a small volumetric flow.
Using this urine diverting toilet, urine is collected in the front bowl, while feces, toilet paper, and other solids are collected in the back bowl. The urine is flushed away using only a small volume of water. This helps conserve potable water and keep urine in a concentrated state. At the building level, urine can be treated as it passes through a urine diverting toilet or urinal, or alternatively, all of the source separated urine produced within a building can be conveyed by urine-only pipes and combined. Once collected, this entire volume of urine that was produced within a building can be stored for disinfection purposes or treated.
For example, within the toilet or urinal, the urine may flow through a cartridge containing sorptive materials that have a high affinity for phosphorus or nitrogen. The nutrients collected within these cartridges are prevented from entering the centralized wastewater treatment plant and can be periodically recovered for reuse.
If urine is collected for storage and treatment, nutrients can be recovered by various treatment processes, such as precipitation. For example, with the addition of a magnesium source, struvite may be precipitated from urine. Struvite is a mineral that contains magnesium, ammonium, and phosphate. This mineral can be used as a slow-release fertilizer.
The separate collection of urine also presents the opportunity to reduce the discharge of pharmaceuticals into the environment. Approximately 70% of the pharmaceuticals we consume are excreted through our urine. Typically, these pharmaceutical compounds are unaffected by wastewater treatment and are therefore discharged into the environment. At the building scale, urine source separation allows us to more effectively target pharmaceuticals for removal from urine, as well as produce a contaminant-free nutrient product.
Overall, urine source separation diverts only a small fraction of the flow from combined wastewater, yet it separates a large fraction of the influent nutrients and pharmaceuticals.
Targeting these compounds in urine not only lends itself to the reuse of nutrients in agriculture, but reduces the pharmaceutical and nutrient loading in centralized wastewater treatment plants.
These reduced loadings of nutrients and pharmaceuticals into centralized wastewater treatment plants minimize the need to treat large volumes of wastewater with advanced wastewater treatment processes. Additionally, it ultimately improves effluent wastewater quality.
So, in summary,
Liquid gold.
Liquid gold is right. That was a great presentation by Kelly and Stephanie. Though I wonder, how can we recover nutrients on a smaller household scale?
Actually, I know a way that I learned from Ryan Shaw when I was a Peace Corps volunteer in Mali, West Africa. His research as part of the Peace Corps Masters International program was on urine fertilization. This is especially important in the developing country context, where over 1.2 billion people lack adequate sanitation, and poor families rely on subsistence agriculture, and fertilizer is very expensive. Let's hear more from Ryan Shaw.
In West Africa, people have been using animal feces as fertilizer for thousands of years, so it's always been easy for me to explain the concept of nutrient recycling. And while people are hesitant to discuss the topic of human feces in Mali or anywhere on the planet, attitudes about urine as fertilizer are slowly changing in many countries in West Africa. And it's because people are seeing how easy it is to use and how well it works. There's even incidents of urine theft in Burkina Faso, where jugs of urine are stolen in the night and returned empty in the morning. It's crazy, I know. I've always talked about urine diversion as this kind of gateway drug to nutrient recovery. It's high in nutrients, urine's low in pathogens, and it's much easier and cheaper to collect safely than human feces. And then wherever latrines are used, urine diversion also keeps latrine pits a little drier, and that reduces odor and also speeds up pathogen die-off. Once people have the habit of diverting urine, it's a much smaller jump to using dry pit latrines, and then even go into composting toilets. So in Mali, we focused on making a cheap urine collector with local materials, and we focused on using a urine fertilizer dose that was sure to show high crop yields. So I went to a bunch of local groups in my town and several surrounding villages and made the case for urine fertilizer. And many puzzled looks and awkward giggles later, I had a small pocket of people that were willing to give it a try. So this is the magic urine collector. Ta-da! The design is borrowed from CREPO, which is a West African organization, and the best modifications came from the Malians themselves. They had tons of great ideas. So this entire collector costs about $3 to $4 US, and the biggest cost is actually this special funnel that was made out of sheet metal by a local blacksmith. That costs about $250. Then the funnel would fit snugly into the mouth of one of these 80-cent big yellow water jugs that were widely available. To prevent odor and nitrogen loss via escaping ammonia, we would tie a rubber strip around the neck, and then we used a plastic bag filled with water to seal the mouth of the funnel. Then if the latrine was roofless, we would cap it off with a lid to prevent rain diluting the urine too much. And there it is, an easy, cheap way to collect urine, and the use was really easy. So we would all learn how to use the collector, dilute the urine, and apply it on crops in the proper doses. This is all explained in nauseating detail in my master's thesis. But arguably the most important piece of urine collection training was teaching the Malians how to experiment by only applying urine to one portion of their fields. This was a big deal because once they started seeing the difference that the urine fertilizer made, they started telling their friends, or if they were embarrassed about telling their friends, people started talking about the differences in crops, and then people started asking questions and teaching each other, and the idea really spread, very slowly, but it was spreading in a sustainable way, and it was really cool.
So we hope you learned a lot about nutrient recovery systems at the household, building, and city level. Colleen, where are you going?
To make a deposit. Hopefully these are the bathrooms of the future.